All right, now we're not going to go on to section 2, but before we do that, I actually forgot that we did not do example 2 from section 1 from topic 10. So let's do that real quickly. This will be a good review. So example 2 asks you to identify the type of solute as either being strong, weak, or non-electrolyte. This is a very simple review or demonstration of the types of electrolytes. And so if I take a look at beaker A, I can see that nothing is ionized. There's no ions in here. And so by definition, this is going to be a non-electrolyte. If I take a look at beaker B, I can see that pretty much every single thing in here is an ion. Yes, there's one compound that is not ionized, but remember the definition of a strong electrolyte is it produces a large number of ions, not necessarily always absolutely 100%. So that would be considered a strong electrolyte. And then finally, beaker C, most compounds are still intact. There's only been a few ions, and so that would be weak. And so hopefully that was pretty simple. We're now going to move on to section 2, which are acid-base models. We're not going to talk too much about acid-base models because Chem 152 is going to cover that a little bit more in depth. But we do want to have at least a basic understanding of the acid-base models. And so let's go ahead and take a look at those. There's actually more models than just what's on the screen here, but we're only going to cover 2. We're going to cover the Arrhenius model and then the Bronsted model, or more specifically, the Bronsted-Lowry model. So if I were to ask a student, hey, what makes something an acid? What makes something a base? I would probably get these general answers. Students would tell me, you would know you have an acid because it's got hydrogen bonded to something. And then you would know you have a base because it's something bonded with hydroxide. And that is a definition that is decent. It gets us to a certain point, but that's not necessarily a perfect definition of what an acid and a base are, but it's on the right track. So under the Arrhenius model out of all the models of acid base is the most restrictive in its definition. So you can see over here, there's 3 models of acids and bases. There's the Arrhenius model, the Bronsted-Lowry model, and then the Lewis model. And you can see the Arrhenius model, by its definition, it's the most exclusive, meaning it's very restrictive. And so based on this model, acids are defined as producing hydrogen ions, and bases are defined as producing hydroxide ions. And so that would be like what we talked about up here. And so is that incorrect? No, that's not incorrect. That is correct. Acids produce hydrogen ions and bases produce hydroxide ions. But the problem is that doesn't cover everything. Like for example, let's take a look at the compound NH3, which is ammonia. Ammonia does have base properties. It is considered a base. But why would it be considered a base? Because there's not hydroxide in the formula. So we need different models, different definitions of acids and bases to include this. And so that's where we get the second one, which is the Bronsted model, or more specifically, the Bronsted-Lowry model. Both are acceptable. So an acid defined under this model is a hydrogen donor, right? It's a hydrogen donor. And remember, hydrogen ions are the exact same thing as protons. They're the same thing. If you're not sure why that is, you can look that up. But you could also say proton donor. But an acid is considered to be a hydrogen donor. And here's the big difference. A base is defined as being a hydrogen acceptor. And so a base is going to be any substance that will take on that additional hydrogen ion. So you can see the definitions are a little different. Does that mean the Arrhenius model is right and then or wrong and then the Bronsted model is right? No, it just means the Bronsted model is a little bit more inclusive with what it considers to be an acid and a base. It's not as stringent in its definitions. So let's take a look at some pictures so you can see what this looks like. So remember I said ammonia, NH3, is considered a base. Why is that though? Like why is that since hydroxide is not in the formula at all? Well, let's take a look at what happens when you put ammonia in water. So first of all, I want to actually point out, notice the reversible arrows. Remember what that means? That means that this is a reversible reaction, meaning it goes in both directions at the same time, right? So that is going to be considered a weak electrolyte because at any one point, it's not all ions. But that's just a review. Let's take a look at what's going on. So on the reactant side, I have ammonia is going to be dropped in water, right? We're going to put ammonia in water. And notice what happens, it gets produced on the product side. You get ammonium and you get hydroxide. How did that happen? What ended up happening? Well, ammonia is considered to be a base, and under the Bronsted model that we just learned, bases do what with hydrogen? They accept hydrogen, right? And so if we think about ammonia being the base and it's going to accept a hydrogen, that means it's going to accept a hydrogen from water. So the hydrogen is going to actually come over here and add on to the ammonia. And that means water, in this example, is acting as an acid because it's donating its hydrogen. Do you see that? Now, what is the result of that? Well, now it's no longer NH3, it's NH4 because it has that extra hydrogen. But notice also what happened to the charge, because ammonia was neutral. There was no charge to ammonia. But when it took on a hydrogen, which remember, hydrogens are +1, when it takes on that hydrogen, it's no longer neutral, it's now NH4 with a +1 charge. Its net charge is now +1. Well, what happened to the water? Okay, water can also be written as HOH, and there's a reason why I'm writing this like that, because this hydrogen at the beginning is what donated to the NH3, and so as a result of that, you end up just with OH. And since water was originally neutral, if it loses a positive ion, that's why it's now -1. And so think about the charges have to be the same on both sides. So 2 neutral compounds on the reactant side means the overall charge is 0, which means the overall charge needs to also be 0 on the product side. So if one thing is now +1, the other thing has to be -1. Couple things I want to point out here. Number one, you see how you produce ions? That's why it's considered an electrolyte. Weak electrolyte, but it's still an electrolyte nonetheless. Also, notice in a roundabout way what ended up getting produced. Hydroxide, right? And that's why NH3 is considered a base. Not because it has OH in its formula, but because it does produce hydroxide when it's dropped in water. Now, remember, this is a reversible reaction. And so, remember, the hydrogen was donated to NH3. It can give that hydrogen right back to where it came from. And it does, actually. It goes back and forth, back and forth. So, if this NH4+, if it's donating the hydrogen right back to where it came from, this NH4+ is considered an acid, but we give it a special name. It's not just an acid. We give it the name of a conjugate acid. Okay? Because it was created, right? It wasn't the original acid, but it's serving as an acid on the product side. It's the conjugate acid. And hydroxide is acting as the conjugate base because it wants to accept the hydrogen back. Okay, so you have those terms, conjugate acid and conjugate base. Let's look at another example. Looking at these same ideas, let's look at another example. So this one, very similar to what we saw before. This time we're dropping HF into water, right? We're dropping hydrofluoric acid into water. And if you take a look at what's going on, first of all, you do have the reversible arrows, so it is a weak electrolyte because it's going to go back and forth. Notice what happened. The hydrogen that was right here ended up donating to water. And so what ends up getting produced after that? Well, it's no longer H2O, it is now H3O. And water was originally neutral, but if it adds on an extra hydrogen, that's why it's now +1. On the same side, HF, when it loses that hydrogen, it's now just down to the fluoride ion. And this was neutral. If it loses a positive hydrogen, that's why you're left over with fluorine being negative. And so HF is acting as the acid, which hopefully that was a little bit clear to see because, begins with hydrogen. So that's the acid. And in this example, water is acting as a base. Do you notice how water can act as either an acid or a base? That is known as being amphoteric. Water is amphoteric because it can act as an acid or a base because of its chemical arrangement. Notice it has the acid part, hydrogen, but it also has the base part, hydroxide. So that's why it can act as both. So in this example specifically, it's acting as a base. Now, it can give the hydrogen right back to where it came from, right? So H3O+, since it wants to donate the hydrogen or give up the hydrogen, what would H3O+ be? It would be the conjugate acid because it wants to give up the hydrogen. And the fluoride ion, fluoride ion, that would be known as the conjugate base because it wants to accept the hydrogen back. Okay, so that's how you can identify what the acid is, what the base is, what the conjugate acid is and what the conjugate base is. Real quickly, I just want to point this out. When you have polyproduct acids, remember polyproduct just means it has multiple hydrogens at the beginning. Like H3PO4, it's got 3 hydrogens. What that means is when it donates its hydrogen, it does it in steps. So, for example, if I took H3PO4 and I dropped it in water, these 3 hydrogens are going to ionize one at a time. It always does it in steps. So if you drop this in water, it's going to produce 1 hydrogen. The leftover is H2PO4. That H2PO4 will then donate another hydrogen, and now you're left with HPO4, and that HPO4 will donate its last hydrogen, and so then you'll be left with the phosphate ion. So I just want to point out that when you have multiple hydrogens, it's always 1 hydrogen at a time. So keep that in mind. So to end this section, we're going to do examples 3 and 4. So in example 3, it says, below are Bronsted acids. What is the conjugate base for each? Remember, what is a Bronsted acid? Does it accept hydrogen or does it donate hydrogen? Bronsted acids donate hydrogen, and they'll always do just 1 hydrogen at a time. So the question's saying, okay, if this is categorized as a Bronsted acid, what would be the conjugate base? In other words, what would be the result of it donating 1 hydrogen? So for this first one, HClO4, this 1 hydrogen is going to be donated. So what gets left over? It's ClO4. And notice the charge. It has to be ClO4 negative because it was neutral and it lost a positive ion. NH4 plus, what ends up what are you left with once you have one of those hydrogens after donating it? Well, you'd have NH3, and since it already was originally positive 1, once it loses the positive hydrogen, it's back down to being neutral. H2O, okay, if it gives up a hydrogen, what are you left with? You would be left with the OH, and it's going to be negative. And then HCO3 negative, if it loses that 1 hydrogen, if it donates it, what are you left over with? You're left over with CO3. This whole thing was originally -1, so if it loses another positive hydrogen, now it's going to be -2. So make sure you're watching those charges. Now in example 4, similar idea, but now we're looking at Bronsted bases. And so Bronsted bases accept hydrogens, and they only accept 1 hydrogen at a time. So what would be the conjugate acid? In other words, what would be the result after it accepts 1 hydrogen? Well, cyanide, Cn negative, if it accepts 1 hydrogen, okay, and we're going to write the hydrogen at the beginning, it's HCN, and it was originally negative, so now it's neutral. SO4 2-, that's your sulfate. If it accepts 1 hydrogen, because it's always just 1 hydrogen, it'd be HSO4, and now it's not -2, it's just -1. H2O, if it accepts 1 more hydrogen, it's now H3O, and now it's going to have an overall positive 1 charge. And then finally, HCO3 negative, if it accepts 1 more hydrogen, it is now H2CO3. It originally was -1, so now it's neutral. All right, that concludes section 2. We'll see you in the next section, section 3.